There is a version of history in which Albert Einstein was wrong. It is a version built on selective memory, on the handful of moments where his predictions seemed untestable, where his theories appeared too abstract to matter. For decades, several of his most significant ideas were not rejected because evidence contradicted them. They were rejected because no one could yet prove them right. This is an important distinction. Being disproven and being ignored are not the same thing. A theory can be set aside not because it fails, but because the instruments capable of testing it do not yet exist. That is not a flaw in the theory. It is a limitation of the era. Einstein published some of his most consequential work in the early 20th century. At that time, the tools available to physicists were crude by modern standards. Within the scientific community, there was a strong preference for ideas that could be tested immediately, with equipment already on hand. Several of Einstein's proposals did not meet that standard, not because they were careless speculation, but because they were ahead of what technology could confirm. Over the decades that followed, as detectors were built and satellites launched, those proposals were tested, and one by one they held. This is the account of 3 ideas Einstein put forward that were dismissed during his lifetime, and the moments when each one was confirmed. In 1916, Einstein completed a full mathematical description of gravity through his theory of general relativity. Within that framework, he made a specific prediction. When massive objects accelerate, they do not simply pull on the space around them, they disturb it. They send ripples outward through space-time itself, distortions that travel at the speed of light. He called these gravitational waves. The prediction was mathematically precise, but it carried an immediate problem. The effects Einstein described were extraordinarily small. A gravitational wave passing through a detector on Earth would stretch and compress the space between 2 points by a fraction smaller than the width of a single proton. No instrument in the early 20th century, or for most of the 20th century, was capable of measuring a change that minute. Because the effect was so small, many physicists treated gravitational waves as a theoretical curiosity. There was a period, roughly spanning the 1950s and 1960s, in which debate over whether gravitational waves carried real physical energy was genuinely unresolved. The mathematics said they existed, but mathematics alone does not settle a scientific question. The project known as LIGO, the Laser Interferometer Gravitational Wave Observatory, required decades of engineering and repeated upgrades before it was operational. On September 14, 2015, LIGO detected a signal. 2 black holes, each roughly 30 times the mass of the Sun, had spiraled into each other over hundreds of millions of years. In their final moments, they released an enormous amount of energy in the form of gravitational waves. Those waves traveled across more than 1 billion light-years of space and arrived at Earth as a distortion measuring less than 1,000th the diameter of a proton. LIGO measured it. The signal matched Einstein's mathematical predictions with extraordinary precision. The shape of the wave, its frequency, its intensity, all of it aligned with what general relativity had described a century earlier. Einstein had not guessed. He had calculated, and the calculation was correct. Einstein's relationship with quantum mechanics is often summarized in simple terms. He did not like it. That summary is accurate but incomplete. Einstein understood quantum mechanics well enough to identify what he believed was a fundamental problem with the theory as it was being developed in the 1920s. The specific phenomenon they were concerned with was what later became known as quantum entanglement. When 2 particles interact in certain ways, their quantum states become linked. Measuring a property of one particle instantly determines the corresponding property of the other, regardless of the distance separating them. Einstein believed this indicated that quantum mechanics was missing something, that there must be undiscovered variables that would restore a more intuitive picture of how the physical world operates. His position was not that entanglement was imaginary, it was that the theory describing it was incomplete. In the 1960s, physicist John Bell devised a mathematical framework that could distinguish between Einstein's interpretation and the standard quantum mechanical one through experiment. A series of increasingly rigorous experiments beginning in the 1980s tested Bell's inequalities directly. The results were clear. Quantum entanglement is real. The correlations between entangled particles cannot be explained by any local hidden variable theory. Einstein's specific interpretation was incorrect. but his instinct about the phenomenon's significance was not. Entanglement is now central to quantum computing, quantum cryptography, and quantum communication. Einstein identified something fundamental before anyone understood what it could do. When Einstein published special relativity in 1905, one of its most counterintuitive consequences was the prediction that time is not fixed. It passes at different rates depending on relative velocity and gravitational field strength. An object moving at high speed or situated deeper within a gravitational well experiences time differently than an object at rest in weaker gravity. This effect is called time dilation. For most of the 20th century, time dilation was treated as real, but practically irrelevant. The speeds required to produce noticeable effects were enormous. At everyday velocities, the difference in the passage of time was vanishingly small. Critics did not deny the effect. They argued it was too marginal to matter outside of laboratory conditions. That assessment changed when the United States developed the Global Positioning System. GPS relies on precise timing. Each satellite carries an atomic clock, and the system calculates a user's position by measuring the time it takes for signals to travel from multiple satellites to a receiver. For that calculation to work, the clocks must be synchronized with extraordinary accuracy. They cannot be synchronized because the physics will not allow it. Satellites in orbit move at speeds that cause their clocks to run slightly slower than clocks on the ground, a consequence of special relativity. They also orbit at higher gravitational altitude, which causes their clocks to run slightly faster, a consequence of general relativity. These two effects do not cancel. Without correction, GPS positions would accumulate an error of roughly 10 kilometers per day. Engineers account for this drift before the satellites are launched. The corrections are built directly into the system using Einstein's equations. Every time a GPS receiver calculates a location, it is relying on the fact that time dilation is a measurable, quantifiable physical effect. Time is no longer treated as a uniform background against which events occur. It is treated as a variable, one that bends and shifts in response to motion and gravity, exactly as Einstein described. The pattern across all three cases is consistent. Einstein's ideas were not dismissed because they were poorly reasoned. They were dismissed because the scientific culture of the time placed a high value on immediate testability. Physics in the early 20th century was shaped by a practical standard. If a prediction could not be verified with existing equipment, it was deprioritized. Funding was directed toward experiments that could produce results in the near term. Theoretical work that depended on technology not yet invented was treated with caution, sometimes with open skepticism. There was also a structural factor. Scientific institutions moved slowly. Peer review, grant allocation, and academic reputation all favor incremental progress over radical claims. A prediction that cannot be confirmed for 50 or 100 years does not fit neatly into the cycles by which research programs are evaluated. The gap between mathematical prediction and empirical confirmation is not always a sign that something is wrong. Sometimes it is simply a sign that the confirmation has not yet become possible. Science is often described as a self-correcting process. That description is accurate, but it omits an important detail. The correction is not always fast. It depends on the development of tools, the accumulation of data, and the willingness of a field to revisit old questions when new evidence becomes available. Correct ideas can remain unrecognized for years or decades. This is not a failure of the scientific method. It is a feature of it. The method does not validate ideas based on their logical consistency alone. It waits for evidence, and evidence, in some cases, takes a very long time to arrive. This means that at any given moment, there are likely ideas currently dismissed that are in fact correct. The history of physics offers no guarantee that every important truth will be recognized in its own time. It offers only the assurance that, if the tools are built and the experiments are run, the truth will surface. Patience is not a glamorous quality in science, but it is an essential one. The value of an idea is not determined by how quickly it can be confirmed. Albert Einstein did not lack confidence in his work, but confidence alone does not determine the fate of a scientific idea. The fate is determined by whether the evidence exists to support it, and whether the technology exists to generate that evidence. Einstein proposed gravitational waves in 1916. They were confirmed in 2015. He raised concerns about quantum entanglement in 1935. The experiments that validated the phenomenon began in the 1980s. He described time dilation in 1905. Its consequences became undeniable when GPS was built. In each case, the delay was not caused by Einstein being wrong. It was caused by the world not yet being ready to prove him right. Science does not always reward the person who is first. It rewards the person who is eventually confirmed. Einstein falls into both categories. The ideas that were once set aside as untestable now form part of the foundation on which modern physics and modern technology are built. Being correct in science does not always mean being believed. Sometimes it simply means being right before the rest of the world catches up.